want to start this video by talking about two corollaries of Theorem 17 that we proved last time. So this first one is really important to know. It comes up frequently, for example, on algebra comprehensive and qualifying exams. All right, so let's suppose that alpha and beta are elements that are algebraic over some field F. Then alpha plus beta, alpha minus beta, alpha times beta, and alpha divided by beta. Here you can't divide by 0. So here when beta is not equal to 0, these are all algebraic over F. So in particular, if you take alpha equals 1, 1 over beta, beta inverse is also algebraic over F. A next corollary is if L over F is an arbitrary extension of fields, then you can take, maybe this isn't an algebraic extension, but you can take the collection of all the elements in L that are algebraic over F, and they form a subfield K of L. All right, so first, it's clear that corollary 18 implies corollary 19, because if you have some elements that are algebraic over F, what do you need in order for those elements to form a field? You need to be able to add, subtract, multiply, and divide. And corollary 18 is exactly telling you that you can do that, that anytime you have two elements that are algebraic over F, you can take sums, differences, products, and you can divide. Okay, so corollary 18 implies corollary 19. So let's prove corollary 18. So the idea is that alpha plus minus beta, alpha times beta, and alpha divided by beta, these are all elements in the field generated by alpha and beta over F. So what do we know about that field? Well, if alpha and beta are algebraic over F, then this field is generated by finitely many algebraic elements over F. And Theorem 17 says that a field extension is finite if and only if it's generated by finitely many algebraic elements over the base field. So Theorem 17 says that this extension is finite. And now, what do we know about finite extensions? Corollary 13 that we already proved says that finite extensions are algebraic. So that means that all of these elements, alpha plus minus beta, alpha times beta, alpha over beta, these are all algebraic over F. Okay, so that's the end of the proof. So the key thing is these two facts, that an extension is finite if and only if it's generated by finitely many algebraic elements, and finite extensions are automatically algebraic. So that tells you this fact, which proves that in any extension, the collection of all of the elements algebraic over the base field form a subfield. All right, so the next thing I want to do is focus on one example that's really important. So we have the rational numbers, and the complex numbers are a field containing the rational numbers as a subfield. So this is an extension. So we can take the collection of all of the elements of the complex numbers that are algebraic over the rational numbers and see that they form a subfield of the complex numbers. Let's call that subfield Q bar. So Q bar is the subfield of elements of the complex numbers that are algebraic over Q. We'll come back and say more about this notation in the next few lectures. This field gets a special name. I think it's actually my favorite field. It's up there. It's certainly in the top few. But Q bar is often called the field of algebraic numbers. And so now we can ask, what kind of extension is this? So that's not like a really well-defined question. There are lots and lots of things you could ask. But I'll pause and erase, and I'll begin at least telling you one property of this extension, which is that its degree is infinite. We want to study this extension, the field of algebraic numbers, as an extension of Q. So the first thing that I want to do is say something about the degree of this extension. So what are some elements that we know are elements of C that are algebraic over Q? Well, those are complex numbers that are roots of monic irreducible polynomials with coefficients in Q. So what's an example? Is x to the n minus 2 is irreducible in Q bracket x for each n. So what does that mean? That means that this field of algebraic numbers contains the nth root of 2 for each n. So this positive real number that you raise to the nth power and you get 2. So if you contain the nth root of 2, then you also contain the field generated by the nth root of 2 over Q. And the degree of this extension is n, because the minimal polynomial of this element has degree n. So what does that mean? That means that this field Q bar has subfields of arbitrarily large degree over Q. It has a subfield of degree n for each n. So there's no way that this extension could be finite. Like it can't have degree 100 because it has a subfield of degree 101. So this shows that this extension is infinite. Okay, it's this infinite extension. C is also an infinite extension of Q. And one question is, are they the same? Is this field of algebraic numbers actually a proper subfield of C, or is it just like a fancy name for C? And it is a proper subfield, and that's the next fact that I want to explain. So an element in C that is not in Q bar, an element that is not algebraic over Q, is called transcendental over Q. All right, so what's an example of such an element? Pi is transcendental, and E is transcendental. These are not in this field Q bar. But I'm not going to prove this for you. This proof is not easy. For one thing, if something is transcendental, it's not algebraic. It's certainly not in Q. And even showing that pi and E are not rational numbers is a little bit tricky. So that's an argument that maybe you've seen before. Showing that they're transcendental is, significantly more challenging. This whole field of transcendental number theory, like proving that things either are or are not rational, are or are not algebraic, is really tricky. It's not something that I understand well. I think it's fair to say it's not something that we as a mathematical community understand super well. Here's an example of an unsolved problem. We know that pi and E are transcendental, so they're definitely not rational. But what about pi plus E? That's probably transcendental, but I don't think that it's currently even known whether or not pi plus E is rational. It almost certainly isn't, but I don't think we have techniques for proving this kind of thing. Okay, so what have I claimed? I've claimed that Q bar really is a proper subfield of C by saying, well, pi and E are in C, but they're not in Q bar. But I didn't prove that for you, so that feels a little bit like a cheat. So what I'm going to do is I'm going to pause and erase, and then I'll give an argument that Q bar really is a proper subfield of C without actually producing an element of C that is not in Q bar. This argument is going to show that Q bar is a proper subfield of C because they have different cardinalities. We're going to prove that Q bar is a proper subfield of C by showing that Q bar is countable. So we know that C is uncountable. Even its proper subfield, the real numbers, is uncountable. So these two fields are not equal because they're not the same cardinality. So this argument is very different than anything I think that we've done so far in Math 206. So this is not the kind of thing you would see on an exam, but it's good to know because it's proving an important fact about this field that is like very much a topic of major study in algebra. Okay, so what do elements of Q bar look like? Every element of Q bar is the root of a monic polynomial in Q bracket x. So what does that look like? It's x to the n plus an minus 1, x to the n minus 1, plus a1x plus a0, where a0 up through an minus 1 are in Q. And if we have one polynomial, it has at most n roots. So that gives it most n elements in Q bar. So this is a little fuzzy, but the idea is that how many elements are there in Q bar? Well, how many elements come from polynomials of degree n? Well, it's at most n times the number of these monic polynomials. And how many monic polynomials are there? Well, we know that Q is countable. So there are countably many choices for the first coefficient, countably many choices for the next coefficient. There's n minus 1 coefficients. You have countably many choices for each. That shows that there's only countably many monic polynomials of degree n in Q bracket x. And each one only has at most n roots. So the number of elements of Q bar that come from roots of all of the monic polynomials of degree n in Q bracket x, that is a countable set of elements of Q bar. But then we'll just go from like n equals 1, n equals 2. We have 1 n for each positive integer. So what are we getting? We're getting a countable union, 1 for each of these n's, of countable sets of elements of Q bar. Given n, we're looking at the set of all things in Q bar that are the root of a monic polynomial of degree n in Q bracket x. And it's a fact that a countable union of countable sets is a countable set. So that proves that Q bar is countable, and therefore it really is a proper subfield of C. All right, I'm going to pause and erase, and then I'll prove one more fact in this video. We'll end this video by proving Theorem 20 in section 13.2. This says, if K is algebraic over F and L is algebraic over K, then L is algebraic over F. So think of L as being like the top field, K as being the field in the middle, and F as being the field at the bottom. If the middle field is algebraic over the bottom field and the top field is algebraic over the middle field, then the top field, in fact, is algebraic over the bottom field. Okay, so what do we need to do? We need to take any element alpha in this big field L and show that it's algebraic over F. And I like this argument a lot because it uses some of the pieces we've been developing. What do we know about alpha? Well, we know that L is algebraic over K. So every element in L is algebraic over K. So it satisfies some polynomial with coefficients in K. So let's write down that polynomial for this element alpha. Let's say that it's an alpha to the n plus an minus 1 alpha to the n minus 1 plus a1 alpha plus a0 equals 0, where these coefficients, an minus 1 down to a1, a0, these are all elements in K. Okay, well, what do we know about these elements in K? These are all algebraic over F because K over F is an algebraic extension. So all of these elements in K are algebraic over F. All right, so the big idea here is we're going to consider this field generated by A0 up through AN and alpha over F. Okay, so this is the big idea that makes this argument work. We know that this field is the field generated by alpha over this field F adjoin A0 up through AN. Okay, I want to pause and say that in the last lecture, we proved this lemma that said the field generated by alpha and beta over F is equal to the field generated by beta over F adjoin alpha. And then I said that that lemma implies this fact is true. And that's what it says in dominant foot. And I thought about it more. And it is not clear to me how that lemma directly implies this fact, even in the case where you have like F adjoin alpha 1, alpha 2, and alpha 3. Okay, we're saying that that's the same as the field generated by alpha 3 over the field generated by alpha 1 and alpha 2 over F. It's really not clear to me how to use just this statement of the lemma to prove that that's true. But it is clear that you can use the same proof strategy to show containment both ways, to show that this really is true. I just think that it's less direct than dominant foot make it seem with the phrasing. So this is a good thing where I would encourage you to write down a fully detailed proof of this fact once. Okay, so that aside, this statement really is true. And what do we know about this field generated by A0 up through AN over F? That is a finite extension of F. Why? Because it is generated by finitely many algebraic elements. That's what Theorem 17 says. A0 up through AN, each one of those is algebraic over F. So this field generated by those set of elements over F is a finite extension of F. Okay, so what do we know now about this extension? The one generated by A0 up through AN and alpha. Let's see what we can say about its degree over F. Well, this is the degree of this field you get generated by alpha over F adjoint A0 up through AN over this field F adjoint A0 up through AN times the degree of this finite extension, the field generated by A0 up through AN over F. The degree of this extension, we know this is finite. We don't really know anything about how large this degree is. It doesn't matter. This is finite. What do we know about this degree? Well, that's like asking for the degree of the minimal polynomial of alpha, where your coefficients live in this field, F adjoint A0 up through AN. And we know one polynomial that alpha satisfies, where the coefficients are certainly in this field, F adjoint A0 up through AN. It's this polynomial star, given by this like starred line here, that has degree n. So whatever the degree of this extension is, whatever the degree of the minimal polynomial is, it's certainly at most n, because the minimal polynomial must divide this polynomial. So this is at most n, and this is a finite number. So this product is finite. So that means that this extension generated by alpha and A0 up through AN over F is a finite extension. And what do we know about finite extensions? Finite extensions are algebraic. So every element in this field here is algebraic over F. But in particular, what's one element in this extension is alpha. So alpha is algebraic over F. But what was the starting point here? Alpha was just like any old element of L. So what we've shown is that any element of this field L is algebraic over F. So that says that the extension L is an algebraic extension of F.